area, which is for actual physically moving your mouth when you speak, which is in frontal lobe. We talked about spatial awareness in the parietal lobe, right? Knowing where you are in space, and the patients who ignore half of their visual world. And the last thing we were talking about last Monday was memory. And you guys might recall, what's the name of the brain area in charge of memory? Hippocampus, right? We were talking about that patient who had the seizures. We took out his hippocampus, and he couldn't form any new memories. That patient was HF. We left off talking about a study that was done on the London cabbies. And you guys might recall London cabbies who have very good spatial awareness and spatial memory. They had actually increased size of their hippocampi. So the hippocampi were structurally bigger. But recall, when they retired, what happened to their hippocampus?
They shrunk back to
they shrunk back. So that gets us into the idea that I want to bring up now, called synaptic plasticity. So this is where we left off. Okay. So the idea of synaptic plasticity. Let's just first of all think about what plastic means. Or think of like a plastic bag or like plastic Tupperware. How would you describe plastic? What is that?
Durable.
Durable, good, pretty durable. What else about plastic? How is it different than something like wood or glass?
They're reusable or
Flexible.
Reusable, yep. Flexible, yep. So think about plastic in the terms of it's more, yes, it's durable, yes, it's reusable, but it's very flexible, right? Unlike other materials like wood, right, like glass, you can't bend it. But plastic is something that's a little bit flexible, a little moldable, you can bend it. That's where the idea comes in with synaptic plasticity. It's the idea that your synapses aren't always exactly the same. They're not the same when you're born, they're not the same when you're 15, they're not the same when you're 16. It's the idea that your synapses can be flexible or moldable. They can change over time. And if you guys might remember just the physical structure of a synapse, if you look at this image, you might recall this is the axon terminal of one neuron, and this is the dendrite of the second neuron. Where do you find the synapse? Yeah, the space in between, right? And what's the name of those chemicals that travel across the synapse? Neurotransmitters, yeah. So that's what we're talking about when we say synapse. And when we say, hey, it can change over time, what scientists notice is that your neuron can grow new axon terminals. It can actually even grow new dendrites. So you can grow and modify the axon terminals and dendrites. Basically related to the behavior that you're practicing. So you guys might have heard of this little phrase called, if you don't use it, you lose it, right? Which is actually true. And you know, there's this kind of push for elderly people to keep their minds active, right? Do things like Sudoku, right? Kind of those brain puzzles to keep their mind active. The idea is that as long as you keep using these connections, right, keep these neurons communicating, these synapses will stay strong and healthy. They'll communicate better, they'll communicate more efficiently, and by doing so, you can actually see, they actually take pictures and they see new dendrites growing, new axon terminals growing. The more dendrites and axon terminals you have, the better your synapse works, the better your neurons communicate, the better that area is functioning, right? So they saw this if you use it, but if you don't use it, the dendrites go away, kind of like in stress, right? The dendrites go away, extra axon terminals go away, your neurons basically start to more or less shrink, and then they don't function as well, and therefore that brain area is not functioning as well. So again, very important, right? Keep using it, keep practicing. You actually see anatomical changes that match the behavioral changes. Right? Okay, questions on that?
Did you say that these, so all neurons can grow axon terminals and dendrites, or is it just in the hippocampus? Or?
No, most of the studies have been done in the hippocampus because that's where you can see the most change. So the question was, can all neurons do this, or are we just talking about the hippocampus? So I said a lot of the studies have been done in the hippocampus because that's where neurons are most likely to be changing a lot. But this can happen all over the brain. So one of my colleagues in grad school studied this in the occipital lobe, and he saw the same thing with vision.
Okay.
As you develop and use your vision a lot, the same neuron growth and kind of robustness occurs in the visual neuron. So again, this can happen all over the brain.
Wasn't it in a previous lecture where we said something about neurons aren't regenerative?
Right, when we say neurons aren't regenerative, or basically if the whole neuron dies,
Okay.
then that neuron can't come back.
Okay.
But as long as your neuron is actually still alive, the core of it, right, the cell body, the dendrites and the axons can modify appropriately. So that's why it's so important. You never want to absolutely kill off the neuron. Once you kill off the neuron, then that neuron is not coming back for the most part. But as long as your neuron is still physically alive, it can barely be alive,
Right.
but as long as the neuron is still alive, it can go through these modifications to get enhanced functioning. Yeah, great question. Okay, so I'm going to save this for a little bit later for review at the end of the lecture, but we're going to look at a case study. But again, I'll do it at the very end because I want to head on and finish up the brain areas, and then we'll go back to that. All right, so we just spent basically, again, the majority of this lecture in the cerebrum. For the humans, that's about 80% of your brain weight. That's all of your higher order thinking, like your seeing, your personality, your hearing, your memory. Now we're moving into a second major part of the brain called the diencephalon. The diencephalon, you can think of it as like the dead center of your brain, deep in the middle in the core. And the diencephalon has three major brain areas, the epithalamus, thalamus, and hypothalamus. So all very close to each other. And the important thing is these three brain areas together often help you with maintaining your homeostasis. So we know homeostasis as a nice, steady, stable body environment. And one of the main examples we started off with homeostasis in lecture number 1 was temperature, right? Body temperature. So when we say, hey, we want to make sure our body temperature is set to about 37 degrees Celsius, it's actually in here, your hypothalamus, that basically sets that temperature mark and tries to keep your body at that 37 degrees Celsius or 98.6 degrees Fahrenheit. Other things that we need to maintain homeostasis of are things like your hunger and your thirst, right? Monitoring those levels. And we'll see in the next lecture, regulation of hormones. Hormones play a huge role in making sure your body is balanced. So we'll see that this area, specifically the hypothalamus, is going to be key in helping regulate hormones, which is, again, a big portion of your homeostasis. One particular feature I want to mention right now about homeostasis is your sleep-wake cycle. So this is done by this little nucleus here called SCN, our suprachiasmatic nuclei. It's actually a sub-portion of the hypothalamus, so it's inside the hypothalamus. And again, this is going to help you control your sleep-wake cycle. What I mean by sleep-wake cycle is what time your body naturally likes to go to sleep and wake up. So for example, how many of you guys are like late night owls? Like you sleep at midnight or later? Like naturally. Okay, how many of you guys are like, no, I prefer a little earlier. Given my own, if I had no obligation, I prefer to go to sleep a little earlier, maybe 10, 11. Yeah, okay, and then think about on the flip side. When do you like to wake up? Let's say you had no obligations in the morning, right? You had no work, you had no school, you had no family, and you just let your body wake up whenever you want to wake up. What time is that? 1, 3, 10, 11. Right? Notice everyone kind of knows what their body likes to do, and it's different for every single person for the most part. Again, that's your sleep-wake cycle, and everyone's sleep-wake cycle is a little modified. That is controlled by this area right here, the suprachiasmatic nuclei. So it's your what we call circadian rhythm, right? What's your rhythm for when you sleep and when you wake up? Now, left to your own devices, most people are not going to be going to sleep at like 8 in the morning naturally, right? And waking up at like 4 p.m. The reason why is everyone's SCN is actually linked up to visual or light input. So that light coming in through your eye and the photoreceptor ultimately also makes it back to the SCN in the hypothalamus. The idea is that your SCN should coordinate with levels of light outside. Logically speaking, when it's light outside, what should you be doing?
Be awake.
You should be awake, right? And if it's dark, you should be asleep, right? So your SCN is trying to coordinate with your outside environment, saying, oh, it's dark, we should go to sleep. Oh, it's light, we should wake up. So that's why everyone kind of roughly is in somewhat the same schedule in that respect. But here's the problem. Think about, especially in healthcare, right? A lot of people have to work graveyard shift, right? You have to work around the clock, right? There's 24-hour care. So if you're on graveyard shift, which is the night shift, right? Let's say 7 p.m., 7 a.m. It's, again, people say, oh, that's not healthy, right? The reason why it's not healthy is it goes against your natural cycle here, the SCN, because again, you're naturally inclined to coordinate with daylight and nighttime. So, how do we get around that? Let's say you have to work graveyard shift. So you're up, 7 p.m. to 7 a.m. There's probably low ambient level of light at your clinic or your hospital. What should you do when you go home to sleep at 8 a.m. in the morning?
Blackout curtains.
Blackout curtains, right? Or eye masks or something. The idea is that you can trick your body, right, into thinking, hey, it's dark outside. No light, then your SCN says, oh, no light, it's time to sleep, right? So that's why those things actually are really important, and it does help your body get that more restful sleep. If you can actually sleep when it's dark, again, because we've got technology that's turn off the light, somehow block off the light, and then when you're awake, be in a more lit environment. Right? Okay. Another aspect to add to this is, well, how does your SCN say, hey, it's sleep time or it's wake time? Yes, it coordinates with light, but it also releases this this hormone called melatonin. And that is actually released from this special gland called the pineal gland. So the SCN tells your pineal gland, okay, melatonin, this is my hormone that's going to help me sleep or wake up. And to show you melatonin release, if you can see this, you might not be able to see it in the back, but you can look on the side screen. What we have here on the x-axis is time. Where the white bar is, that's daytime. Where the black bar is, that's nighttime. On the y-axis are the peaks of melatonin. So the pink are peaks of melatonin. When do you release more melatonin, day or night?
Night.
Nighttime. Notice every single time it's night, you get a peak release of melatonin. So basically your body says, oh, it's nighttime, release melatonin. Melatonin, hormone that circulates around your body and basically tells your body to get into sleep mode. Now you might have heard of melatonin before. You can actually just get it over the counter, right? If someone has issues sleeping, one of the first things they can do is just go to your local drugstore and you can actually just buy melatonin supplements. When would that person want to take melatonin supplements if they have trouble sleeping?
Right before you sleep.
At night or right before they want to go to sleep, right? Because the idea is that maybe your body's not producing or releasing melatonin when you want to go to sleep, so you can supplement with the over-the-counter melatonin. Yeah, Daryl.
What disorder is that when someone has unnatural levels of melatonin release?
Yeah, so what is the disorder specifically called? So I don't know, like insomnia is just the general name with difficulty sleeping, but just because you have insomnia doesn't mean it's that it's all a melatonin problem. So I don't know, the exact, if they know for sure that it's a melatonin issue. But a lot of insomniacs do have issues regulating their melatonin release.
But the light controls the melatonin release.
It should. They should all coordinate together, right? The light should help with the SCN. The SCN tells the pineal gland it's time to release melatonin because it's dark. So again, for us, right, because we have artificial light, we can stay up later and not feel as sleepy in the sense because we've got light coming in, right? It doesn't have to be from the sunlight for us. All right. Okay, so that's a little bit about diencephalon. Remember, one of the key things is controlling your homeostasis. We gave some examples of homeostasis in your body. All right, a third brain area that's critical is the brainstem. So you might remember from anatomy, brainstem is divided into 3 major regions. We have midbrain, which is the most superior part of the brainstem. We have pons, which is in the middle. and then we have the medulla oblongata, which is the most inferior part of the brainstem, and in fact, it merges with the spinal cord. All right, so these three areas make up the brainstem, and if you were to have to identify one of the key functions of the brainstem, what would you say?
The basics of life. Is
What? Aaron kind of lots of look for the different things.
Autonomic function?
Okay, autonomic function, but lots of brain areas do autonomic function. Coordination? Yeah, not totally incorrect, but if there was one word you had to use for a brainstem, it would be survival. Survival. In fact, yes, it's autonomic, yes, it coordinates with your nervous system, but one critical thing about brainstem itself is it is absolutely necessary for survival. What do you absolutely need to be doing to be alive?
heartbeat, breathing.
Breathing. What else?
Heart.
Heart pumping. So you need to be breathing the oxygen, right? And then your heart needs to be pumping the blood, which helps circulate the oxygen and the nutrients. So when we say survival, you should be thinking, okay, two things absolutely critical, breathing and my heart pumping. So when we get to the cardiac system and the respiratory system later, we'll actually come back and relook at the brainstem because they are going to be critical. So now, if you look at the location of the brainstem, again, it's the inferior portion of your brain, and again, this is your neck right here, right here. So if you notice if you have any sort of accident, right, and the person is unconscious, or even if they're conscious, one thing they're always careful about is stabilize the neck. Why do you want to stabilize the neck? What's close to the neck? The brainstem. And again, survival functions, right? Coordinating heart rate and breathing. So that's one reason why they're always so careful about that neck region. If you want to protect the brainstem, you want to make sure your brainstem is not damaged or going to get more damaged by moving around. And another thing you might see happen at like an accident is they might actually shine a light into the patient's eye. Here's what they're doing. They're checking for a reflex. And remember we did that lab on reflexes? Right? How can reflexes be important for us? What can they tell us?
That your nervous system is working
Yeah,
properly?
that your nervous system is working, right? And one thing is to see if your brain is working. So here's why they're shining the light in your eye. They're trying to see if not only your nervous system is working, but specifically if your brain stem is working. And again, they want to know if your brain stem is working because that's controlling your heart rate and your breathing rate, which is actually keeping you alive. So we're going to try this little experiment. It was actually the one in your lab manual, but we didn't do it then because I said we'll do it here in class. Okay, so what we're going to do is we're going to try and mimic this test, and it's a little